Hello, how are you? We are Brandon Munoz and Josue Cortez, and today we will explain to you about a method called area moment method, which is within the geometric methods to be able to calculate deformations or displacements. This method, like double integration, is used to calculate two different displacements. Speaking a little about their history, these were proposed by Otto Moore and later revised and formalized by Charles E. Green in 1872, which is why some authors know them as Moore's theorem or Green's theorem. For this method, or theorem as we want to call it, just as in double integration, we have equations that will help us solve the exercise. Now that we know that we have two displacements, angular and linear, we obtain the following equation for the angular displacements.
This equation gives us a lot of data, and you will say why. For these two reasons. With the function m on EI, we can graph the moment diagram with the m. And by dividing it by the bending stiffness, we obtain the moment diagram on EI, which we can use to calculate these deformations. Now, how do we calculate the rotation? Just like that? Well, no. In order to calculate the deformations, they will always ask us to measure the rotations between 2 points. On the deformed beam of the beam, which are tangent, and at the intersection of these an angle is formed which we can call θ. And how do we represent this mathematically? Well, now our integrals will have limits since we will be integrating with respect to 2 points. So our first equation of the area moment theorem is the following. The angle between A and B is equal to the integral from A to B of the equation of moments on the bending stiffness with respect to x, which represents the rotation or change of slope between two sections of a beam. We must take into account the signs which are positive in the counterclockwise direction and negative in the clockwise direction. Therefore, the moments will be positive as they will be counterclockwise. Now, how do we calculate linear deformations? Following the same methodology, we have our second equation.
We have that t is the distance or difference between two lines. One is a tangent drawn through a point and a vertical line that passes through a point on the beam. But how can we apply these equations easily in the following way? The linear deformation between A and B is equal to the integral from A to B of the moment equation on the bending stiffness times the first moment of inertia, all this with respect to x. This integral represents the distance or linear displacement between 2 points.
Why is it called moment area? Well, the areas that are formed when making the moment diagram on the bending rigidity will be of great help to us in order to calculate the angular deformations. We must calculate their areas, and the sum of these between the modulus of elasticity will be equal to the angle to which we are relating them. Then, for the linear displacements, also calculating the areas of each figure formed by the moment diagram on A, now we will multiply them by the first moment of inertia. And in the end, we divide all this by its modulus of elasticity, which will give us its linear deformations as a result.
And it's whispered that soon, if we all call the tune, then the piper will lead us to reason. And a new day will dawn for those who stand long, and